Hi friends, welcome to this class. In this video, we are going to discuss about this methyl orange and phenolpthalein. That also comes under the synthetic dyes, right? So let's go to this, right? First, let us discuss about this methyl orange, right? So what is this methyl orange? It is nothing but helianthine. It is also called as the like that, right? So let us see how this methyl orange is prepared, right? So this is our benzene ring. So here SO3H. I hope you know the structure. S double bond O OH, right? So this is the structure SO3H, right? Instead of writing all like this, just I'll write SO3H simply, SO3H, and here it will be having azo group, N triple bond N, nitrogen is having positive charge and fluorine will be there, right? So this and when it reacts with this one, what is this? This is our NN dimethyl aniline, right? So this is our NN dimethyl aniline, and this is nothing but sulfonilic acid. This when react with this NN dimethyl aniline, I will get this methyl orange, right? So let us see the reaction, right? So how this reaction happens? So this reaction is simple, same as I have explained in previous class. So here this act as, see here, positive charge is there on nitrogen, right? And this compound is called azo compound, right? N double bond N, right? Diazo we call it as, right? So this is electron deficient, so it acts as electron deficient. Electron deficient means I'll try to write electrophile, right? Because it is electron deficient. Whereas this is electron rich, because nitrogen is having low pair, it can resonate like this, right? So it will be electron rich. So what happens, since it is electron deficient, so form pi bond, it takes through this carbon, it takes the electron density, and this pi bond shifts on nitrogen, and nitrogen becomes neutral, right? So what I am doing, just I am doing electrophilic substitution reaction, right? So what we will get, let us see that. So we will get this thing. So here I can SO3H, right? And here N, now it became double bond N, and here there is attack like this. So here this gets positive charge, here double bond and nitrogen with lone pair, two methyl groups are there, right? So this positive charge is stabilized by this pi bonds here, resonance. So pi bond shifts here, plus charge comes here, then it can give its lone pair and stabilizes, right? If I want to write the stabilization structure here, with this only canonical structure I am going to write, because these things are the basics you know. So I will directly write like this, and nitrogen with positive charge like this. It is the stabilization structure. But if you see this is anti-aromatic. This ring is the right, so benzene ring was there, it is anti-aromatic. Why it is anti-aromatic? Because it has got 4n pi electrons, means 4 pi electrons it has got, 2 and 4, and all are in conjugation, all are in planar, so it is anti-aromatic. So to make it aromatic, so driving force is aromatization is the driving force, because we know the stability order. Aromatic compound is more stable than non-aromatic, then comes the anti-aromatic. This stabilization we know. So to do this aromatization, so next step is aromatization is the driving step, in which this H will go as proton, this bond shifts here, this bond shifts here, again nitrogen becomes neutral, right? This is the thing. So I will write that product. So what we get is our methyl orange. Instead of writing circle, I will put like this, right? Everything is same, SO3H, and here azo group, diazo group, and double bond N, and here I have got again my benzene ring restored, and I got NN dimethyl. So this structure is nothing but my methyl orange, right? In room temperature only, not room temperature, but if in common thing only it looks like orange color, so we call it as methyl orange, right? NN dimethyl orange, right? So this is the synthesis step of this methyl orange. Let us see how it acts in presence of base, in presence of acid, that thing we shall see. So this is the structure, right? So with this I am going to start. So when I treat with this base OH minus, so see here SO3H is there. If I want to write it elaborately, I will write like this: S double bond O and H. So this H is acidic. Why it is acidic? Because if I remove that H, oxygen gets negative charge. That will be stabilized by these two electron withdrawing groups, right? So oxygen are highly electronegative, they can stabilize that negative charge easily. So if I remove this H, I will get like this structure: SO3 minus and other things as it is, benzene ring here, azo group, diazo group, and here I will get this thing, right? So this color, if you see, it is also orange in color because only H is removed. It was also orange, it is also orange. If what happens if I treat this with acid, right? So this methyl orange, when I treat with acid, see here, just I will write here only, just I will remove this thing, see. So acid will be there, this nitrogen will be having lone pair, so it will donate like this, right? So this nitrogen becomes positive. Shall I write here or here? No problem, let me write here. So this nitrogen becomes positive, right? So as nitrogen becomes positive, it takes this electron density. So this nitrogen becomes positive, so it takes this electron density. Here positive becomes, so this bond shifted here. So this positive charge is here, now it shifted here, right? If I want to write the structure, it becomes like this here. Other thing same, SO3H, because acidic substance means H will be there as it is. So here N got H, so now here N, right? But here double bond is there. Final canonical structure I am writing, right? So it will be like this, right? If you see the color of it, right, it will be red color, right? So what we saw, the same methyl orange in basic media it was orange in color, but in acidic media it is red in color. So it is changing its color, right? This thing you agree. So this methyl orange is dye. We are studying this in dye only, but we never use this methyl orange as a dye, but we use it as acid base indicator. So indicators we have studied, acid base indicators. Why we use it as acid base indicators? Because see here, in basic media the same methyl orange which was orange, it is orange here in basic media, right? Whereas in acidic media it is red in color. So it indicates whether the solution is acidic or basic, it will indicate, right? So if the solution is basic, then the methyl orange will be orange. If the solution is acidic, then methyl orange will be red, right? In this way it indicates, so we use it as indicators. So we use this methyl orange as well as this phenolphthalein also we use as acid base indicators. And you may ask, sir, then we will study this in acid base indicators chapter, right? Why we are studying in synthetic dyes? So why I am taken these things in synthetic dyes means these methyl orange and phenolphthalein can't act as dyes, they act as only indicators. You may ask, why sir, why it can't act dye? Because methyl orange is also having orange color, right? So the problem is this methyl orange is there, right? It is having orange color, but it is not resistant to soap, nor water, nor light. Whenever I take this methyl orange which is orange in color, if I expose it to light, it will vanish, right? I have told in the first class only, I have told dyes will have the characteristic thing, the 3 points. One is it should have color, second thing it should be resistant to water, light, everything, right? And it should attach to the fabric, these cloths, right? Fabrics very strongly it should attack. So those are the 3 conditions or the characteristics I have explained, right? So this will want to be satisfied. It will be, if it falls on our cloth, if I wash with water and soap, it will vanish, right? Because of which we never use it as a dye, but here we use it as indicator because it indicates. In basic media it will be orange, in acidic media it will be red. So this is about methyl orange. It is also called as halitine, right? So this is the structure you need to remember, right? I hope I made it clear to you. So further, before going further, see here, in acid base indicators, those videos are available in my YouTube channel. There you can see that I have given you the range of this indicators, right? There I have told that phenolphthalein its range is around 8 to 10 pH. Here range will be in terms of pH, right? And this methyl orange is there, right? Its range is around 4 to 6. Means within this range, if a solution is there, it can't indicate. If pH of the solution is less than 4, then it will think that it is acid, then it will show the red color. If the pH of the solution is more than 6, let us say 6.5, then it will indicate, it will assume that the solution is basic, then it will show that orange color, right? But within this 4 to 6, if the solution pH is 5, then it can't indicate, right? So that's the problem with this indicator. Same with phenolphthalein, its range is 8 to 10. Below 8, it will think all are acid. Below above 10, it thinks that all is basic, and in between it can't indicate. But we know that in pH scale, we know that 0 to 7 and 7 to 14. So this is our acidic, and this range is called base, right? So acidic strength we measure in 0 to 7, but this indicator, see, for it less than 8 is acid, but if we speak truly, less than 8, if I consider 7.5, it will be basic. But these indicators, that's the problem with these indicators. That thing you should remember. So I felt it like to tell here, so I told it, right? So we studied about methyl orange. Let us see how we synthesize this phenolphthalein. So I have told it is also a acid base indicator. So phenolphthalein, what is this? Can you tell? This is benzene ring, here COOH is there. So it is benzoic acid. If I keep in one more COOH here, so you will call it as phthalic acid. Phthalic acid, right? So instead of writing like this, I will write it like this. Let me have the chalk piece. Yeah, I will take like this COOH here, and instead of writing COOH like this, I will write like this COOH. When I heat it, this thing you might have done in lab. What you do in China disk, you will take this phthalic acid, you will place it, above that you will place a paper, small pores you will do, and you will place a inverted funnel, and just when you heat below, those things are comes above, and the water will be lost, right? So when I heat, there will be loss of water, H this and OH will lose, so I will get this thing. Can you tell what is this? CO. What is this? Phthalic anhydride. Right. So this is phthalic anhydride. So using this phthalic anhydride, I will prepare this phenol. How I will prepare? I will just tell you. So this is the story for this phthalic anhydride. So how I will prepare? See here. I will take this phenol. Yes, this is phenol. Everywhere H will be here. I will show only this H, and I will take one more molecule of phenol. So I am going to take 2 molecules of phenol, and that phthalic anhydride which I got, I will take that. So this is my phthalic anhydride. So yeah, right. So what I will do, in presence of concentrated H2SO4, I do the reaction. Right, little bit warming I will do. What happens? See, H form this, O form this. So all these three will lose as water molecule H2O. So there is one molecule water is lost. So this H2SO4 act as a dehydrating agent. It helps in removal of water. So we call it as dehydrating agent. Right. So what we will get? See here. This one I will get. So here this water lost, so carbon, so it will be attached to carbon, and this will also attach to carbon like this, right? Other things as it is. So here one OH, here one OH, and here it is anhydride, right? So I will show that, and here COO group is there, and other things as it is, benzene ring here. nothing, just everything I have left same only, just I have removed water and 2 hydrogen, so water molecule I have removed, so this carbon is this one, right? So other thing same, oxygen, C double bond O, and here benzene ring, there also benzene ring, right? So this is the structure of phenolphthalein. So what is this? This is our phenolphthalein, right? So this is the phenolphthalein. So how it acts as acid base indicator, let us see that, right? So I hope you got it. Now you should be able to write the structure of phenolphthalein without seeing. See here, just you can write like this, right? See here, double bond, here OH, here on carbon, like this you can do. Again phenol, here OH, double bond. Other things here to this carbon, right? Here O is there, here COO, right? And it is attached to benzene ring like this, right? So here COO. So what happens? So this is our phenolphthalein. Then what I will do? So this phenolphthalein is there, right? It is colorless, or white I can call, white crystalline solid it will be there. When I treat this in basic medium, basic means OH minus, what happens here? So this proton, phenol proton will be acidic. So this base will take this proton. So negative charge comes on this oxygen now. So see here, resonating structure. It will resonate like this. This pi bond will shift. This carbon oxygen bond will break. Right? If I write that structure, see. When I treat this in alkali medium, OH minus, I will get this product. See, just I will write here. So carbon, here double bond came. Other thing remained as is, double bond here, double bond O. Right? Here OH is there, and everything is same here, this side, and here this bond is broken. Right? So this bond is broken. Other things remains as it is. Here double bond O and O minus is there, right? So if you see, this structure is quinone structure, quinone. Because of this quinone structure, this will be pink in color, right? So what I wanted to tell is, this phenolphthalein is colorless. In basic media, it will convert into pink color, because of which it acts as a acid base indicator. In basic solution, it converts into pink color, so it acts as a acid base indicator, right? I hope you got it. Why it is pink in color? Because of this quinone structure I have called. This is quinone. These structures are called quinone. So in next class I will explain the theories of theories of color. Why those substances are color. There I will come with different theory, and one of the theory is this quinone theory, in which the compounds which are having like this structure, quinone structure, they will tell that those will be colored, right? So this is the example for that quinone theory. In phenolphthalein is a good example. In basic media it will be pink, in acidic media it will be again colorless, because this phenolphthalein is there, right? So it is having acidic proton, so it comes under acidic dye also. Acidic dye, as it contains acidic proton. But we never talk it in terms of dyes, because I have told these are what? These are not resistance to any light or the soap, right? So we never tell them as a dye. So we use them as a indicators, as they indicate in acidic solution this phenolphthalein will be colorless, basic solution it is pink in color. Whereas methyl orange in acid solution it is red in color, and basic solution it was orange in color. So these are the two things we have discussed. I hope you understood this. In next class let us see some theories, why that color, what is the theory behind the color of the dyes, right? That thing we shall see in next class. Till then, take care and have a great day.